most of the time there is no class afterwards, so this should be fine. Okay, so last time we talked about the weak disorder phase, and we saw basically two things. So first, one thing was that if you defined the average measure, okay, as we saw that, well, in a sense, this average measure was absolutely continuous with respect to the simple random walk, but uniformly in n. Okay, meaning that if bk goes to 0 as k goes to infinity, Pn, sorry, Pn bk. Okay. Limit when k goes to 0 of Pn. If you have a sequence, if you have a sequence of events whose probability with respect to the simple random walk goes to 0, then the probability also goes to 0 with respect to the average measure uniformly in n. Okay? So basically, this kind of thing tells you that anything which is typical for the simple random walk is typical for the directed polymer measure. Okay, this is if weak disorder holds. Okay. But on the other hand, what we have proved is that if you look now at the non-average measure, okay, you can find events that are very likely for the polymer measure and very unlikely for the simple random walk, and vice versa. Okay. On the other hand, there exists A and omega such that okay, P and omega is smaller than exponential minus Cn, and P and beta omega A and omega C is smaller than exponential minus Cn. Yeah, we just saw that these things were going to 0. Okay, but the truth is that, yeah, I mean, these events they corresponded, if you remember, to large deviation from the mean. Okay, from the law of large numbers, so they have exponentially small probability. Okay, if you remember, An was that. The sum from n equal 1 to n of omega n. Yeah, the set of x, so that this is larger than lambda prime beta over 2. Okay, and basically, from the proof of that, okay, what you could get is that typically under the polymer measure, like this sum for typical paths was equal to lambda prime beta times n. Okay, so the idea that in the weak disorder phase, the polymer measure, it lives on a very sparse set of paths. Okay. because the proportion of paths that satisfy this is exponentially small. Okay, but the idea is that this sparse set is kind of well spread, you know, on omega n, so that on large scale you don't really see that. You don't really see the fact that your support is really small. Okay, so this property of sparseness, the fact that it's well spread, okay, this property of being well spread, okay, this kind of indicates this a little bit. Yeah, the problem is that you have this just for the average measure. So what we will do today is to prove something more convincing. We will prove convergence to Brownian motion of the rescaled polymer path in some. Okay, we will show a convergence in probability, and I will comment on that, what this means exactly. Okay, so the first thing I will do is basically to recall you what convergence to Brownian motion means. Okay, so a brief recall about Donskoy's invariance principle. Okay, and then present you the proof of Donskoy's invariance principle for directed polymers. And this will rely on something called the Harris inequality that some of you might know. So Harris or FKG inequality. Okay, we'll see that and prove that. Okay, so Donskoy's invariance principle. For the simple random walk on Z. Okay, so any question? Okay. Okay, so we consider X a simple random walk on ZD, so we call P the distribution. And let me now extend the range of X, okay? I will also define X for real numbers. So I just defined XS to be equal to XS minus N, Xn plus 1, S minus N times Xn plus 1 plus N plus 1 minus S Xn if S belongs to N plus 1. Okay, I mean, you can check. I mean, I put the bracket closed here, but you can check that this definition, I mean, when S is equal to N, this is just Xn is equal to Xn. Okay, so this is just, I'm just making this a piecewise linear function, okay, by extending it to 1. Okay, and then I define Xn. Okay, and I will just look at times between 0 and 1. This is just Xns divided by square root of n, S in 0, 1. Okay, so what I'm doing here is I'm speeding up time by a factor n and renormalizing space by a factor square root of n. And this thing here, xn, okay, well, it's a random variable, but it takes value in some space, and I call this space C0, 0, 1. It's just the set of functions from 0, 1 to R, such that theta 0 is equal to 0, and theta is continuous. Okay, so yeah, for short, I think I will just use calligraphic C for this space. Okay. I'm not saying anything special. I'm just saying that xn is a continuous function and that it starts from 0. So now the important thing is that I want to equip this with the supremum norm. So here, this thing is just the max from S in 0, 1 of theta S. Okay, and now what is Donskoy's theorem? Okay, so yeah, basically due to a couple of Russian mathematicians in the 50s, including Donskoy and Kolmogorov. And what it says is that x s n, s in 0, 1, converges in distribution when n goes to infinity towards a random process. Okay, so this means okay, and where Bs, S in 0, 1, is a standard d-dimensional Brownian motion. Okay, so by definition, this is a unique process, okay, that takes value in C, okay, and so it satisfies the following. B0 is equal to 0, okay, continuous trajectories. Okay, so basically it takes values in calligraphic C. It has independent increments. And BT minus BS, it is distributed like, well, a centered Gaussian with a covariance matrix T minus S times the identity. Okay, or if you prefer, all coordinates are independent, and each coordinate is a Gaussian of variance T minus S. Okay, so now I want to insist a little bit on this. What does it mean? So So convergence in distribution here, it means that for all phi from C to R, limited and continuous. Okay, this thing it's a Banach space, so you can define continuous functions from C to R. You have that. The limit when n goes to infinity means that the expectation of phi of xn converges to when it goes to infinity, when n goes to infinity, to the expectation of phi of, well, the Brownian motion divided by square root of t. Okay, and q here is just the Wiener measure. Okay, the expectation with respect to Brownian motion. Okay, so perhaps some remark about this. So I think most of you, like me, you've been introduced to convergence in distribution, not in the general framework of metric spaces, but rather on R or RD. And perhaps the proof of some statements you saw was specific to R. But there are some things that are quite generic. So let me give you one remark. Okay, so it is sufficient to prove this thing for a good subset of function phi. Okay, you don't have to prove it for all phi, you just need to prove it for a good subset of function. So for instance, phi Lipschitz and bounded is sufficient. Okay, so why is this sufficient? Well, the reason is the following. So if phi is continuous, K included in C is compact, and epsilon is positive, okay, then there exists psi Lipschitz such that so the first thing is that phi minus phi is smaller than epsilon on K, and 2 psi is smaller than phi. Okay, I mean, 2 is easy to, if you find a function that satisfies 1, it can satisfy 2. You just limit it by K and minus K, and we're done. To find the reason why you can find a function that satisfies phi, it's basically Stone's theorem. Okay, so like Lipschitz continuous function on a compact they are dense. Okay, so if you have this, then what do? Take Km such that Q of Km converges, okay, Km such that Q increasing such that Q of the union of Km is equal to 1. Okay, so the reason why you can find this is basically, I don't know, law of iterated logarithm for Brownian motion. Okay, you take Km that are basically trajectories with some modulus of continuity multiplied by m, okay, and then taking m go to infinity, this probability tends to 1. Okay, and then you take psi m such that psi m minus phi smaller than 1 over m on km and psi infinity smaller than phi infinity. Psi m, okay? And basically, once you have this family, okay, you have that star for every psi m implies star for phi. Okay, this requires a little bit of work, but it's really similar to what is done basically when you prove these kind of statements for convergence in distribution on R. Okay, and yes, in the same manner, basically, you can restrict here to a countable family. Okay, and perhaps, well, not something for which I will give a hint of proof, but what convergence in distribution means here, it's true on R, but it's also true here. Okay. What you have is that there exists okay, so what do you have? You have there exists coupling. So let's call it I don't know. Yeah. Mu n, okay, on C, okay, such that mu n A times C is equal to P n omega beta xn in A, and mu n C times B is equal to Q of B. Okay, so there is a coupling between your two probabilities. Okay, such that the first marginal is the law of xn, and the second marginal is the law of B. Okay, and such that, so it's a sequence of coupling such that for all epsilon larger than 0, okay, the limit when n goes to infinity of the probability that xn minus b infinity larger than epsilon is equal to 0. Okay, so convergence in distribution, it means that you can construct the two processes on the same probability space in such a way that with large probabilities they are close to each other. Okay, and again, this has to do with the topological properties of this thing. Okay, the fact that, oh yeah, basically what makes things work is that, yeah, I don't know if the space is separable, but at least the support of the Wiener measure is separable. So you can find a dense countable set, and from there you can cook up a coupling like this. Okay. Any question concerning this? Okay. So okay. Now let me tell you what we are going to prove. Donskoy's theorem for directed polymers. Okay, so what is it? Okay, so let me write what we are going to prove. So for all phi from C to R, limited and Lipschitz, limited, bounded and Lipschitz, the limit when n goes to infinity of E n beta omega phi xn is equal to Q phi b over square root of d. In probability. Okay, so this is what we are going to prove. Okay, let me tell you what this implies. So actually, here I'm putting Lipschitz because this is going to be convenient at some point in our proof. But like because of what I've said, putting Lipschitz or putting continuous here, it's the same thing. And another thing is that here, this converges in probability. So from that, you can infer that there is a subsequence that converges almost surely. Okay, but a priori, this subsequence depends on phi. Okay? However, because of what I've said here, or because of what I implied here, somehow you only need to show this for countably many phi. So by a diagonal extraction argument, basically, this can, if you take the right subsequence, okay, and here, I gave an, yeah, I think I'm a bit messed up because, okay, let's change a, okay, let's use n from now because I will use the little n from the index in the sums over the omegas. Okay, so a consequence of that, we are not going to explore it, but that is that. Sorry? Yes. Which is okay. This is okay. So why do you renormalize by the same thing here and there? Well, it's only because the path which is relevant here, remember, it's the part which is in omega n. So it's just the first n steps. This is the only thing that has physical relevance. What happens after n is just simple random walk. So for instance, and this is what we are going to see in the proof, here, if you take n much larger than this n here, okay, then you're not proving anything because the first few steps that are affected by the polymer measures, you don't see them in the scaling limit. Okay, so this result is meaningful. Well, this means that you're just looking at things that are affected by the. Okay, and yeah, I mean, if you want to put something which is smaller than n here, this works as well. But I don't think this is super relevant. Okay, so if you want, this result would also be valid if you have infinity here. Okay, and you can check it from the proof. I don't think this adds much to the result. This is the relevant thing. Okay, and there exists nk such nk k larger than 1 subsequence such that with probability 1 okay, for almost every omega for all phi continuous E n k beta omega phi xn is equal to yes, limit when k goes to infinity. Or in other words, p nk beta omega converges to q. Okay. So yes, if you take a subsequence, what you have is that almost surely U convergent distribution. Okay, so another way to formulate this is that the distribution of x and k converges to q weakly. Okay, here the important thing is really the order in which you put things. So for almost every omega, the convergence here is simultaneous for every phi. Okay? Okay, and another direct signification of this, okay, is that basically, yeah, you can have a coupling such that you can have a coupling such that this goes to 0. Okay, which is kind of this thing here, okay, without taking subsequence, it's equivalent to that. Okay, so you can find a random coupling between the two measures such that basically, in some sense, the trajectories of xn and of b are close. Okay, so all these comments just to make it clear that this is a strong result. Okay, in spite of having just this convergence in probability, I mean, like, okay, you may want to say, okay, perhaps I would like to have this almost surely, but really physically you don't get, it is not more meaningful. because you're not really interested in this sequence here. Like for every n, you're considering a different state space. Okay, so the joint law of these things, it's not really meaningful. Okay, and convergence in probability, it also means that if you conserve the marginals and you modify the joint laws, you can have convergence almost surely. So, like when you see this kind of statement, I think it's not worth the try to try to prove almost sure statements, because in terms of meaning, they are equivalent. Okay, so yeah, now let's do some math because we haven't proved anything today. So okay, let's introduce the main tool to prove this. So yeah, so this theorem here. Okay, there are some earlier versions, but this version is due to Comets and Yoshida in 2006. Okay, just the same paper I mentioned before, in which monotonicity in beta was proved. Okay, and this was also in this paper that this comment about the infinite volume measure were made. Okay, if you want to check the references. The proof that I'm going to present today is from last year. And yes, so it's based on the Harris inequality. So let me present that first. So Harris-FKG inequality. Okay, so why two names? Well, basically, FKG is something more general, okay, and more difficult to prove also. So yeah, this easier version is due to Harris. Okay, so okay, so what is it about? Well, it's basically okay. Harris inequality is something that tells you that increasing functions on product spaces are positively correlated. Okay, so if you look at the covariance between two increasing functions on product spaces, they are okay. So so let me tell you what I mean by product space by increasing, and okay, and write a statement. So the product space we are going to consider is Rm. Okay, but here you can replace this by any product. What's important is that you want to have a total order on each of. So basically, having a total order means you want each of your marginal to be isomorphic to R, or to be isomorphic to a subset of R. So there is not a big loss of generality here, in considering just R. And so we are going to equip this with an order okay, and we say that X is smaller than Y. It's a partial order if for all I between 1 and m, xi is smaller than yi. Okay, so not the lexicographical order. What we are considering really is coordinate-wise order. Okay, two things are ordered if you can compare all the coordinates. So of course you have many pairs of points which are not. Okay, it's not a total order. You have many pairs of points for which you don't have x smaller than y, neither y smaller than x. Okay. Okay, and now you say that f from Rm to R is increasing if if 2 points are ordered, then the values of f are ordered. Okay, and here this is the order on R. Okay, so what's the FKG inequality, the Harris inequality? So if mu is a probability on R, and F and G are increasing function, okay, from Rm to R. Okay, so we are assuming either non-negative or in L2 of mu m. Okay, this is just for the sake of things being well defined. And then what we have is that the integral of fg d mu m is larger than the integral of f d mu m integral of g d mu m. Okay, so well, this is what I meant by saying that f and g were positively correlated. Okay, and one remark, because so yeah, taking the same measure on all coordinates is convenient for the proof, because writing indices is not super well, the nicest thing to do when you're on the board, but works also with mu m replaced by product from I equal 1 to m of mu I, okay, whereas these mu I are probabilities. Okay, so the important here is just, I mean, it's really valid for any product probability space. Okay, you just need the probability on Rm to be a product probability. Okay. So I'm going to write the proof, but like FKG inequality, okay, the proof is really smart. Here, once, okay, the proof is by induction, and we already know that the result is true for m equal 1. We have proved it some time ago, perhaps last time, no, two lectures ago. So we just have to prove the induction step, and the induction step is just a matter of really, yeah, looking at things the right way. Okay, so proof. So m equal 1, already done. Okay, this is this coupling argument. So now we need to do that. M implies m plus 1. And for this, okay, I'm going to take, okay, I have f Okay, so we are going to do we are going to consider f from Rm, okay, f and g for Rm to R plus. If you want to prove the L2 case, okay, well, if you know it for R plus, basically you know it for bounded functions, because here you can shift things by a constant in this, and then you can do dominated convergence, okay, to get things to the limit on both sides. So there is no loss of generality by considering this. Okay, so this is what we are going to consider. Okay, I'm going to allow for this. Okay, and this is what I'm going to prove by induction. But of course, adding the value plus infinity doesn't change anything to our thing. Because if the value plus infinity is allowed with positive probability, basically you get infinity larger than infinity. Okay. So now, given a function f, I will define two auxiliary functions. So yes. So like when I have x in Rm plus 1, I will write it as x m plus 1. Okay? And I will define two functions. So I will define f x from R to R plus, and well, f x u is equal f x u is equal to 1. Okay, I should write it in the other direction, but okay, this is the definition of f x u. Okay, so it's just a function. So for x in Rm fixed. Okay, so this is one of the function. Now I'm going to define f bar from R to R plus. Okay, here union plus infinity. And f bar of x, it's equal to the integral on R of x u mu du. Okay.
O domínio da f da g é Rm ou Rm mais 1?
Rm plus 1, yes, thank you. Yeah, we want to prove the inequality, okay, at rank n plus 1. So, okay, and yeah, basically we want to use induction, so we are going to use the result for f bar, and also we are going to use the result for m equal 1. Okay, so let's write things. Any other questions or typo to be noticed? Okay, so yeah, so what's this? Mu m plus 1. Well, you can write it as the integral on Rm, and then the integral on R, and then you have f x m plus 1. Okay, let me write. Okay. Fx u g x u mu du, and then mu m dx. Okay, I mean integrating with respect to mu m plus 1, okay, it's, well, integrating with respect to this, okay, just by definition. And then I've just rewritten my functions. Okay, so now I put brackets here, and well, the important thing here is that both fx and f bar are increasing. Okay, assuming that f is. Okay, so this is just, okay, for fx bar, this is just the definition. For fx tilde, this is just the definition. For f bar, well, you take the definition and then you integrate it. Okay, so because fx is increasing, I can just use the result for m equal 1 here and say, well, this is larger. Okay, so this was equal, and now this is larger than the integral over Rm of f bar x g bar x mu m dx. Okay, now I use, well, the assumption, the induction hypothesis. So this is larger than the integral over Rm of f d mu m times the integral of over Rm of g d mu m. Okay, and now, I mean, you just rewrite this as an integral and use Tonelli again, and then this is just what you want, the integral over R m plus 1 f d mu m plus 1 Okay, so like lots of equations and like big displays and lots of indices, but nothing really deep going on here. Okay, so now, yes, I think, okay, we will have time for this, and yeah, if we don't, this is not a problem. I will do some. I will just finish the proof next time. So, let me get you a first corollary of this Harris inequality before moving to the proof of convergence through Brownian motion for directed polymers. Okay, so. Any question about the proof? So corollary. So if phi from R to R plus is C1 and concave, then beta phi Wn beta omega is, well, non-increasing. Okay, so not a new result. Okay, we have already proved it. If you remember, using convex comparison, just to give you an alternative proof, to give you an example of the kind of use you can make for FKG inequality. Okay. So, proof. So we are looking at the derivative of this, and we want to show that this is well, we want to show that this is non-negative. Okay, sorry. We want to show that this is non-positive. Okay. So, okay, if you admit that you can derive within the expectation, okay, which is I mean, your C1 and concave, so the derivative of phi is limited. Okay, so there is not so much going on here. So if you admit that you can derive inside, well, this is. I'm just using composition rules here. So this is what I will get. Okay. So now once I have this, okay, this is an expectation, so I will put again, this is expectation with respect to the simple random walk. So I will put again d beta inside the expectation. So I will get the expectation, then the expectation, then I get, so I've already done this once, so I should be able to write it. Well, okay, let's do every step so that we don't make a mess. So, exponential. Phi prime W and beta omega. Okay, and now when you derive the exponential, you get the sum from n equal 1 to n, and here you get omega n xn minus lambda prime of beta. Okay, because what you have in the exponential is beta omega minus lambda beta. Okay, and then you get phi prime wn beta omega. This thing does not depend on x, right? So you can just put it inside the expectation. Okay, and now you can use Houdini. Yes, and you see, I made the same mistake again. So. When you take the derivative, you get this, but you also get the exponential. Okay, so now what we need to show is that for all x, okay, the expectation of the sum from n equal 1 to n omega n xn minus lambda prime beta well times the exponential of, okay, so let me write it minus beta h n omega x. Okay, minus n lambda beta. And then you have phi prime wn beta omega. Okay, so you want to show that this thing is negative, and then you're done. Okay? So why is this negative? Well, because of Harris inequality. So why is it so? Well, okay, you need to show that you have a product of functions that have different monotonicities. Because you want negative correlations, so you need one thing which is increasing, one thing which is decreasing. So this thing, okay, it's a decreasing function. Okay, and I look at it. Okay, there are several ways to see it, but let's use the version of Harris inequalities that we have proved. Okay, with a product where all the marginals are the same. So it's decreasing as. Okay, so here I will put. Okay. So I will not prove this. I will prove this, but here I will condition to x and x not in xn. Okay, so I'm conditioning to the environment. Sorry. I'm conditioning to the environment outside of this trajectory. Okay, or if you prefer, I'm just averaging with respect to these guys. Okay, x is fixed. So really, yeah, I have a product measure on r to the n. Okay. So now, if you take this thing, and if you consider this as a function, so this is decreasing as a function of omega m xn n equal 1 to n. Okay, if you fixed all of the parameters as a function of these parameters, it's a decreasing function. Okay, and this is an increasing function of omega n xn n equal 1 to n. This okay. This was there. But yeah, this is an increasing function of. Okay, and I have this exponential thing in the middle, but this thing here, I'm going to consider it there. Okay, so I'm just considering here that mu is equal to well, okay, mu of a, no, it's equal to okay. I'm just considering this as a probability density as before. Okay, so well, I have a product measure. I'm taking the average with respect to a product measure. So what I have is that my conditional probability well, I know that it's smaller, okay, using FKG, okay, for, if you want, this and minus this. Okay, this is smaller than, okay, I have some conditional thing here which corresponds to the phi prime, but I don't really care about it. And here I have expectation of, well, exponential sum of n equal 1 to n, beta omega n xn minus lambda beta. And here I have omega n. Okay, n. Yes, this is omega n xn minus lambda prime of beta. Okay, but the important thing is that, well, the average of omega under the measure with this probability density is exactly lambda prime. So this is equal to 0. Okay, so just to say, this thing, you can prove it using convex comparison, but you can prove it using Harris inequality. And this is actually the original proof. So. Any question about this? Okay, so now let's prove our convergence to Brownian motion. So okay, I will set m to be equal to n to the 1/4. Okay, and I guess I will need to fix phi from C to R, which is Lipschitz. Okay, and for commodity, I will just consider that okay, that it takes value in 0, 1. Okay, it's not a lack of generality. I mean, if I have a bounded phi, okay, I can just add the infinite norm and then divide by twice the infinite norm or something like that, and I will put myself in that case. And everything that I'm considering, it's the conversions that I'm considering. Of course, it's preserved by affine transformation of the function. So, okay, and well, we are going to show two things. So first, we want to show that P and beta omega and P m beta omega are similar in a sense, and I will come back to that in a minute. Okay, and second, and this is perhaps the easy part, under Pm, only the first m steps of x are modified. Okay. What I mean modified is that the law is changed with respect to the original law of the simple random walk, and therefore So yeah, under PM, basically, you're just modifying the distribution of the first m steps. But these first m steps, okay, they can transport you only to a distance which is little o of square root of n. Okay, so you don't see them in terms of time, okay, because of course m is little o of n. But also you don't see the transversal displacement implied by these m steps. So therefore, after renormalizing, basically, xn is very close to what you should see for the simple random walk. And therefore, yeah, Donskoy's principle for this, it can be deduced from the simple random walk. Okay, so these are going to be the two steps, okay, and this one is, well, the one which is where you actually have to do something which has to do with your assumptions, okay, so. I always forget to say about this, but I mean, like, everything that I say, it's when Wigg's disorder holds, okay? Okay. So, So let's see in practice how these two steps are, how the proof is decomposed in terms of these two steps. So, well, we have to show that the limit when n goes to infinity of the expectation of E and beta omega phi xn minus E phi xn. Okay, let's put Q phi b is equal to d is equal to 0. Okay, so the idea is that using the triangle inequality, we can split this into three things. Okay, so you have that E and beta omega phi xn minus Q phi b brackets here. This thing, well, it's smaller than, okay, first I take En here. And En here. Okay, so this is. Then I take Em here. And E here. And then I take E first and the Wiener measure in the end. Okay, so I have three terms. Okay. So 3 is going to 0 just because of well, convergence of the simple random walk to Brownian motion. Okay. So we just have to prove that 1 and 2 go to 0. And yeah, 1, this is the important point. And 2, well, this is where I'm going to use basically that phi is Lipschitz. This is going to help me. Okay, I'm just going to use a coupling argument. Okay, so let me prove that 1 goes to 0. Okay, and for this I will need a lemma. Okay, this lemma is actually, okay, so lemma. And for this lemma, no need for weak disorder, but I don't think the result is interesting if you don't have weak disorder. So. Okay, so what does this lemma say? Well, let's consider G. How did I write it? Okay, yeah. Okay. This is just for the sake of. Okay, you don't need G to be. You could take G to be a function of the whole trajectory, but somehow, okay, we don't need that for what we want to prove, and this will be helpful for me to write things in a compact manner. Okay, but and the result is that then the expectation, okay, and larger than m. Okay, here I'm not imposing that m is equal to n to the 1/4. Okay, and what I have is that W n G minus W m G is smaller than the expectation of Wn minus Wn. Okay, so here I'm this WNG. It's just when I define WNA, it's just Wn times expectation n beta omega of j of x. Okay, or if you prefer, the expectation with respect to the simple random walk of sum from n equal 1 to n beta omega n xn minus lambda beta. And then g of x. Okay, so it's just your partition function, but integrated against the function g instead of being integrated against the unity. Okay, so what does this lemma means? Okay, and let's assume that we have weak disorder. So yeah, if okay, by the argument we had, you know, when we defined the infinite volume measure, basically, you know that WNG, it's a martingale and it's uniformly integrable, just because WNG it's smaller than WN. Okay, I mean you can think of G as an indicator function if you want. So it's uniformly integrable, so you know that it converges in L1. What this result tells you is that, well, not only it converges, it's Cauchy in L1, but like the way it's Cauchy, it's uniform in G. Okay, and this is going to be super important because what we want is exactly a result of this type, but for a G that depends on n. Okay? Like this here is really like Gn of x, okay, for some Gn. Okay? So so what's the proof of this? Okay, so first thing to remark is that well, yes, is it true? Yes, I think it's. Okay, so I can write the absolute value here as twice the positive part minus x. Okay. And here, if you look at, so in particular, if the expectation of x is equal to 0, then the expectation of x is equal to twice the expectation of x plus. Okay, and here, what you have here in the absolute value, it has expectation 0. Okay, like the expectation of W and G, well, it's really the expectation of Jx. Okay, so it does not depend on n, so therefore these two things cancel out. Okay, and here these two things they have expectation. Okay, this is just this is just Fubini, you know. When you take the expectation, well, you put the expectation inside, and this disappears because this exponential here has expectation. Okay, so we are just going to prove this, but with the positive part instead of absolute value. Okay, now. I write Wn minus Wm. I can write it as Wn G minus Wm G plus what's remaining. And what's remaining is Wn G bar minus Wm G bar, where G bar is 1 minus G. Okay, I mean, Wn, okay, it's when I'm integrating 1. So what's missing here is integrating 1 minus G. So the important thing is that because of my assumption, G bar is non-negative as well. Okay. Okay. So now I can look at the positive part. Okay, and what I can say is that I'm just going to use this, which, so if I look at the positive part of A plus B, well, this is larger than the positive part of A plus B. Is it always true? No, perhaps this is not true. This is absolutely not true. Which is good because if this was true, I wouldn't need FKG. So let me write things in detail. Okay, so yeah, how did I write things? Okay, I'm taking the positive part. Wn minus Wm plus. Okay, it's larger. Okay, so here I want to put the indicator that Wnj is larger than Wmj. And now I want to put this in here. So let's see why this would be true. Okay, so what I'm saying here is that A plus B plus okay, it's larger than A plus B indicator than A is larger than 0. Okay, so you have two cases, either A is positive or A is negative. If A is positive, then this is true. Okay, and if A is negative, this is also true. All is great. Okay, so perhaps there is a better way than just checking case by case, but this is the only thing that comes to mind right now. Okay, so now, yeah, this thing is Wng minus Wmg. plus, so this is what we want, okay, in terms of the inequality. Now we just need to show that the expectation of this is non-negative. Okay? So now, when you look at, so this is where the fact that G, if you look at W and G, okay, this is equal to the sum over X in omega n. Okay, here I'm using clearly X to denote sometimes infinite random walk, sometimes a random walk with n steps. And in that case, when I apply G to X, it's only to the first n steps. But I think this abuse of notation is not too much of a problem. And this is just exponential sum from n equal 1 to n, beta omega n xn minus lambda beta. And 1 over 2d to the power. Okay. So the important thing now is that W and G is increasing in every omega n x. Okay? If you consider it as a function of one variable and you fix all the rest, it's an increasing function. Okay, so in particular, it is increasing in omega n x, and I will take n from m plus 1 to n. Okay, just fix the environment up to time n, up to time m. Okay, and look at what the rest is. Well, this is an increasing function. Okay, so well, this is also the case for this, simply because this is a constant. Okay, I'm not considering this, what's happening up to time n, m into the variables. Okay, and W and G bar minus W m G bar. Okay, just because G bar, because the important thing here is that you want your coefficients to be positive. Okay, and you know, if G depending on more than n steps, okay, I mean, you would just have a finite sum, and here you would have an expectation condition to the first n steps. Okay, so here I'm composing two increasing functions. So this is also an increasing function. Okay, so for this reason, what I have is that the expectation of W and G bar minus WM G bar times the indicator that W and G is larger than WM G. Knowing Fm, okay, knowing the environment, okay, just by Harris inequality, this is larger than the expectation of Wn G minus Wm G knowing Fm. Here you have the expectation of, well, okay, if you want the probability of W and G larger than W and G knowing Fm. And this thing here is equal to 0. Okay, just because this sequence, it's a martingale sequence. Okay, so if this is equal to 0, then this is equal to 0, then also the expectation of everything is equal to 0. Okay, and therefore, you conclude that the expectation of the positive part here is larger than the expectation of the positive part there. Okay, and then with a linear transformation, you obtain this. Okay, so the idea here is not super complicated. I mean, basically, you're saying, okay, I want to control this increment. This is something plus something. But the other thing I have, somehow, it's positively correlated with that. So that adding it will increase my L1 norm. Okay, the positive correlation, you have it in the L2 sense, but okay, so this is the reason why this is true. Okay, and now let's try to use it to prove what we want. So let's do it. Okay, so so let's define phi n as follows, okay? Phi n is just, well, the composition of phi with the transformation that transforms x into xn. Okay, so we know that the expectation of W n phi n minus W m phi n is smaller than the expectation this. Okay, and we know that this thing go to 0. Okay, so things seem to be in a good shape. Okay, so let's write what we want to bound. Okay, so we want to show that phi xn, we want to bound this. We want to show that this goes to 0 when n goes to infinity. Okay, remember that m is really m of n because it's equal to n to the 1/4. So, okay, this thing, it's bounded by 1 in absolute value. So really what you need to show is a convergence in probability. You need to show that what's inside converges to 0 in probability. But what's inside, okay, it's really Wn phi n divided by Wn minus Wm phi n divided by Wm. Okay, and this thing okay, so this is 1 over Wm Wn phi n minus Wm phi n plus, and then I have W. Okay. Yeah, W. Okay, Wm phi n. Okay, no. Yeah, no. 1 over W n minus 1 over W n. Okay, so this converges almost surely to 1 over W infinity. And this converges to 0 in L1, okay, just because of this. So yeah, you have a product of something, of one thing that converged to in probability to one thing that converges in probability to 0. So it's an easy lemma to show that this converges in probability to 0. Okay, and here, well, this converges almost surely to 0, so in probability. And this is, well, okay, this is smaller than Wm, which converges almost surely to W infinity. Okay, so all of this converges in probability to 0, so in particular, well, it also converges in L1 just because it's bounded. Okay, so I think we are missing step 2. Okay, so let me do it. So now we need to show that basically this is close to what you would get for the simple random walk. And let's do it for a coupling argument, using a coupling argument. So okay, any questions so far? Okay, so let me set mu, which is equal to P m beta omega times P. Okay, so product measure on the space of random mode trajectories. Okay, and I let x be the first coordinate and y be the second coordinate. Okay, x and y. So now I define x tilde n, which is equal to xn if n is smaller than m, and it's equal to y n minus ym plus xn if n is larger than m. Okay, I have two definitions for n equal m, but they are the same. Okay, so my claim now is that xn is distributed like Pm beta omega. Okay? And, well, the reason why it's true is that if you look at xn n equals 0 to m, it's equal to xn n equals 0 to m. So the first m steps have the right distribution. And if you look at x m plus k minus xk, okay, it is independent of xn n equals 0 to m and distributed as a simple random walk. But this is also the case of okay, if you look at the definition of the polymer measure, if you look at the definition of PM, it really doesn't change the distribution of the increments after step M, okay, and it doesn't change also the fact that they are independent of what happened before. Okay, so for this reason, these two processes, they have the same distribution. Now, the difference is that what you have is that x minus y, okay, xn minus yn, it's smaller than m. Okay, it's a 1 norm. It's smaller than m for every m. For every n. Okay? Just because, okay, just because it's the case, okay? Okay, just because it's not the case, you need a 2. Okay, so that in particular, what you have is that x n minus y n, well, it's smaller than m over square root of n. Okay, so it's smaller than n to the 1/4. Okay, I should have introduced some integer rounding when defining m, but this is not really important. Okay, so in particular, you have that phi of xn minus phi of, okay, there is a 2 here, of yn. Well, this is always smaller than c times m over c n to the 1/4. Okay, where this c depends on the Lipschitz constant of phi. Okay, and we're done. We are done because if you look just because of this. Okay, what you have is that P m beta omega phi of xn minus P phi of xn. Well, this thing this is, okay, put absolute value. This is equal to mu, okay, of phi of x n minus phi of y n. Okay, and okay, then you can put the absolute value inside, and you get this is smaller than. Yeah, there is a minus here, right? N to the minus 1/4. Okay, and you get this convergence to Brownian motion. Okay, so this is very nice, and this ends the lecture for today. Let me give you okay, it might seem ridiculous, but one consequence of this convergence to Brownian motion, okay, is the following: is that the limit when n goes to infinity of the expectation of the max over x in ZD of P n beta omega x n equal x this is equal to 0. Okay, just because, well, if your trajectory converges to Brownian motion, the distribution of your trajectory converges to Brownian motion, then the endpoint of your trajectory converges to a Gaussian. The Gaussian has no atom. So, yes, the result, okay, because it's a scaling limit result, it does not give you any information on the rate of decay. Okay, it doesn't tell you that this decays like n to the minus d over 2, okay? In fact, this is false, actually. It doesn't decay like n to the minus d over 2. But at least it gives you this, okay? And because we are going to show that something in the other direction in the strong disorder regime, this is kind of nice to recall. And also this thing, okay, it was not something you could deduce from the statement I have given you at the beginning of the class, okay, and that we proved last time. Like this kind of, any statement on the average measure cannot tell you, give you this kind of information. Okay, so next time we are really going to study strong disorder.